So at long last, we're going to try and work out what the transformations should be that replace these. So in a minute, that's all going to become history. Let me rub out my aeroplane. So now we're going to do less philosophies of physics and more calculations. I'm afraid that the flavour of the lecture is going to change a little bit. In fact, now is a good time for me to say that during these lectures there will be quite a lot of little bits of algebraic manipulation. And you might sit there thinking, this doesn't feel like geometry to me, this feels like algebra. And I understand that. It is possible to do quite a lot of special relativity in a purely geometrical way, but it's quite hard actually, and so my recommendation is that you first of all do the algebra and then sit back and think again. And so I promise it really is geometry, even though it will feel a little bit algebraic sometimes. So the Lorentz transformations. We're going to be using the standard configuration, exactly this. We're going to destroy all of that, right? Well, not quite all of it. Those two stay, but everything else goes. So how do we begin? So we begin by thinking about, and this is the discussion I was having just now, thinking about inertial frames. These two frames of reference are both inertial. That means that if there is a free particle somewhere, just it's not being acted on by any forces, it's just minding its own business, then it will move with constant speed in a straight line. And both of these observers will agree about that. They will agree that it's moving in a straight line with a constant speed. Right? They're both inertial frames of reference. In particular there, and that must be true for any particle. In particular, therefore, straight lines must map to straight lines under the new transformation that we're looking for. It must be a mathematical transformation that preserves the straightness of lines. Okay? Otherwise, they would disagree, wouldn't they, about free particles always moving in straight lines. So we're looking for a mathematical transformation that maps straight lines to straight lines. So it must be linear. Okay? Must be linear. And in particular, x dashed must be some linear form in the other coordinates. How have I done this? Yes. I'm going to focus on x dashed for a moment. I'll work out t dashed and y dashed and z dashed in a minute. So if straight lines map to straight lines, then it must be a linear transformation. Any other mathematical transformation involving any nonlinear function whatsoever will bend a straight line, won't it? So it must be linear, so it must look like this. Okay, so now when x and t are both 0, so remember when t was 0, that was when the two frames of reference, the two spatial frames, were coinciding. This one was here on top of this one. So if you're at x equals 0 and t equals 0, then you must also have x dashed equals 0. Because that was the moment when the two frames of reference were the same, actually. The one moment when they were the same. And that must be true for any y or z. Doesn't matter where you are. And in particular, therefore, the only way that can happen for any y or z is if b and c and e are all 0. Whoops. So that's progress already. So we now know that x dashed is, how have I got this? Oh, no, I don't want to do that yet. I want to do one more thing first. Sorry. Okay, so actually we can just strike those out. I want to do something else now. I want to say if x equals vt, so now you're choosing a point in this frame of reference whose x coordinate is v times t, then you can see that what that's doing is it's actually recording the position of this origin here. This is the place where x is equal to vt. In other words, x dashed must be 0. Okay, so now you put that into here and you get that tells you that so 0 must be a vt plus dt, right? And therefore, have I done that right? Yeah, that's right. And therefore d is minus va. So now we know, coming back, putting it all back into here, we know that x dashed is ax minus vat, and I write that as ax minus vt, and then I change the letter a to a new letter. And I'm going to call it gamma, because that's what everybody calls it, okay? Everybody. I don't know where it came from, probably somewhere in maybe Lorentz's work, or I don't know where it first came, but quite early on, this constant, well, it's not going to be, it'll depend on v actually, but this multiplier here was given the name gamma. I just called it a because I wanted to just use the alphabet here, that's all. You would have thought I was mad if I'd put gamma here, right? So I'm changing it to gamma now. This is just a relabeling. Okay, so we've got x dashed is gamma x minus vt. But we don't know gamma yet. It's some multiplier, but we don't know what it is yet. Now we're going to do something, and this is a very simple piece of argument here. Now we're going to do something clever. If you imagine this arrangement here, suppose you flip around, rotate around the y-axis so that z goes right round into minus z and x goes right round into minus x. And suppose you do the same for this one, so that z dashed goes right round into minus z dashed, and x dashed goes right round into minus x dashed. Then actually And then you think of this frame as being at rest, then this one is moving away in that direction at velocity v. Okay, and it's exactly the same arrangement, in fact. Exactly the same arrangement. It's just that you've relabeled things. In other words, this equation will still be true under the following relabeling, and I've written it out in the notes. You leave t alone, all right? You change x, you exchange x and minus x dashed. You leave y alone. And you exchange z with minus z dashed. So you're exchanging the two. You're changing your mind about which of these two frames of reference is at rest. That's what you're doing. So when you do that, I don't know what to call it, flipping around of the coordinate systems, and you look at that expression there, you'll get x equals gamma x dashed plus v t dashed. Right. So if you do those things to that equation, you get this equation. So if this equation is true, which it is, we've just worked it out, then so must this one be. And we're going to use these two equations to finish the calculation. We're almost there, actually. But before we do the rest of the calculation, suppose we insisted that t dashed equals t. We're not going to, but just for a moment, suppose that we did. Suppose we were trying to be Einstein, and then we just got too frightened at the last minute. No, t dashed must be t. Then what happens if t dashed is equal to t? Then you can see that if you add these two equations together, you'll end up with gamma equals 1, basically. So so this is an aside, if you like. If t dashed equals t, then you get, have I got that right? Then you get gamma equals 1, and you are back in Galilean transformations. Okay, because if gamma is 1, then x dashed is x minus vt, and you're back here. So now we want to write down the crucial fact that the velocity of light is the same in one reference frame as in the other one. And we do that like this. We say, whoops, x equals ct if and only if x dashed equals ct dashed. Right, that's saying that the two frames of reference, so if there's a particle of light moving through here, both frames measure its velocity as c. Any questions? So if you put that back into here, if you put x dashed equals ct dashed in here, you'll get ct dashed equals gamma, and then you have c minus v times t. Right, that's from here. So x dashed is ct dashed, and x is ct. Right. So you get that. And you do the same thing here, and you get ct, whoops, equals gamma c plus v t dashed. So that's ct dashed and that's ct. And now you look at these two equations and you multiply them and strike out the common tt dashed. So you get c squared equals gamma squared c squared minus phi squared. And if you play with that for a moment, you find that gamma is 1 over the square root of 1 minus phi squared over c squared. So now we found what gamma is. So in particular, it's not 1. Okay. In the Galilean transformation, gamma was 1. Here it is, 1 here. We found it something different. We haven't finished yet because I've only worked out this bit. But we've already discovered that it's going to be different. Okay, it's already different from the Galilean transformation. And I hope you agree that the deduction, the process of deduction from those two principles is not difficult, right? The difficult thing is being brave enough to start the process, which Einstein was. And then actually maybe, well, perhaps I will go through a little bit of this. What next? Where shall I go? I'll go over there. I'll rub out the configuration, but you need this. You need this in your heads. Okay, I need this space now, I think. So I'm just going to do a little bit more algebra. I now need to work out what the t dashed. So we did not assume that t dashed was equal to t. And maybe it is, maybe it isn't. We should be agnostic at this moment and just find out, okay, by just doing the same sort of analysis. So we can eliminate, what do we do? Let me just check. We can eliminate x dashed between these two equations. Right, so we put this expression in here, and then we solve for t. So in other words, we get x equals gamma into gamma x minus vt plus vt dashed. Right? Have I done that right? Yes. And then if you solve that for t dashed, you end up with t dashed equals gamma t minus vx over c squared. And I've missed out a little bit of algebra here, but I'm sure you can do it. And in fact, it's the next exercise. Okay, is fill in the algebra here. All you need to know is high school algebra, and you need to use this expression for gamma. It only works because of this expression for gamma. Okay. All right. And then finally, so we know we've now done that one. T dashed is not the same as t. It's given by this expression. It's not difficult to show that these two, in fact, survive. You go through the same sort of argument. You say y dashed must be a linear expression in the other coordinates, and you just do some very quick argument, and you find out that it must actually just be y, and the same for z. So I'll miss that out. If anybody wants a reference, I can show you where to find that. So you've got, where shall I write them? I'll write them all here. So you end up with the following four equations. T dashed equals gamma t minus vx over c squared. X dashed equals that. Y dashed equals y. And z dashed equals z. And that's the Lorentz transformation for the standard configuration. And it's sort of downhill all the way from here in this lecture course. The remainder of our time is going to be working out the consequences of this transformation. Okay, so a good question would be, if we've been so, what's the word, iconoclastic as to destroy the Galilean transformation, why did it take so long? I mean, if time really does not satisfy, if t dashed is really not equal to t, and if x dashed is really not equal to x minus vt, how come we didn't notice until the Michelson-Morley experiment? How did we manage with all of the physics from Galileo up until 18 whenever it was? And as you pointed out, the answer is that although philosophically this is profoundly different from that, because time is now mixed up. In practice, for small velocities, this, where's gamma? Over here. The velocity of light is 300,000 kilometers per second, right? Which is quite fast. And nothing we do in our ordinary lives gets anywhere. So all of the velocities that we're used to, even jet aircraft and so on, they're much, much smaller than this, and it's squared. So this is in general going to be a very small number indeed. It's going to be, you know, very, very, very slightly bigger than 1 gamma. And so this term is almost, in our everyday experience, this term is going to be 0. This is going to be basically 1. This is going to be 1. And so we've got the Galilean transformation. So that's a nice thing, actually. That's a sort of reassuring thing. It explains how we managed for so long and how we continue to manage in our, you know, I mean, when you do, for example, a lot of everyday calculations in physics today, you don't use you only use the Lorentz transformation if you know that you've got relative velocities that are some measurable fraction of the velocity of light. If it's just sort of the velocities of a train, I was arguing with somebody about the light from a train, well, it's not going to make any difference. So that's why we didn't know. That explains why we didn't know. We'll see more about that in a little while. I've got another exercise coming up, which is, so this is the transformation from S to S dashed, right? And so as an exercise, it's a piece of algebra really, is to calculate the inverse. It's just a piece of algebra. In other words, calculate t x, y, z in terms of t dashed, x dashed, y dashed, z dashed. Switch the. I'll give you a clue. Y is equal to y dashed. Okay. It's not hard. It's just an exercise, just to get you familiar with these transformations. That's all. It's an easy exercise. Okay. Now, the next important feature that we're going to need from these equations. I'll say goodbye to poor old Galileo. Is you can take differences or derivatives and you get the following useful expression. It's the sort of obvious one. Wrong. Delta t minus v delta x over c squared, and the obvious those are finite differences, but the same is true for derivatives. Okay, you can just replace it all. Delta can go to d throughout, and just take the derivatives. You're being harassed, I see. Another useful thing you can do, and we're going to do this quite a lot, is instead of writing it all out like this, we're going to use slightly more sophisticated mathematical notation. So I'm going to write a vector, a four-dimensional vector. Whoops. Right, and that's going to be just another way of writing CT x, y, z. Notice that I've included the c as a multiplier for the coordinate here. Turns out that simplifies quite a lot of expressions. And in terms of that vector notation, then we can write this, that x dashed a is a matrix, which I've written L, A, B, X, B. So I'm using summation on that index in the usual way, where that matrix L is this. So it's going to be, this is easy to check by looking at those equations. Minus gamma Gosh, did I do that right? Yeah, that looks right, doesn't it? So that's the Lorentz transformation in the form of a matrix. Okay, that's the Lorentz transformation for the two frames in standard configuration. And once you incorporate into the first coordinate, instead of thinking of the first coordinate as time, you think of it as c times time. Then this is what the transformation looks like. That's easy to check. And again, it's an exercise, actually. It's in my notes. It says, exercise, do this, right? Show that this is the right form for the transformation. OK, so now I want to answer a question that's been sort of in your minds, I think. A couple of you referred to it earlier on. This is the Lorentz transformation for the special case of the standard configuration. So what, this was your question, wasn't it? So what do you do in general, you see? Suppose your two spaceships are not lined up like that, right? They're doing something else. What do you do? So the general case will be this. To get the transformation from one spaceship to the other spaceship, you first line them up, then you do that transformation, and then you undo what you did initially when you were lining the two frames of reference up. In other words, what you might have to do is the following sequence of events. A spatial rotation and translation. And then you might also do a time translation, because the two clocks, they're made in the same clocksmith, right? The identical clocks, but they might not have been set at the same time as each other. So you might have to do a time translation. Getting through the chalk. And then after you've done that, you do the standard Lorentz transformation. So that's this thing. And then you have to undo these to get back to the original configuration that you were in. So you might have to do another time translation. And another spatial rotation. And translation. You might not need all of these. It depends on the initial configuration, but that's the general case. You might need to do all of that to get from the two spaceships have to be inertial frames, so they're not accelerating with respect to each other, and they both agree on free particles moving in straight lines. Okay, but apart from that, they could be doing anything. But this is how you get from one to the other by this sequence. Now it turns out that they're all of those can be written in this form. Not quite in that form, but nearly. Just a minute. So all of these can be written in the form x dashed of A equals some matrix M A, B, X, B, plus some vector, which I've called W in my notes. I called it W. I was going to call it V for vector, but V appears elsewhere, so I've moved on to W. Okay. Now, so I'm claiming that this transformation will take care of all of those. How do we do that? Well, let's first of all make sure that we can take care of this one. So obviously what we do to get this transformation is we put W equal to 0 and we make M that matrix. Okay, so then this is perfectly capable of performing that special standard Lorentz transformation. If we want to make this do a spatial rotation and translation, then well, a translation would be easy. If you wanted to translate a spatial translation, then all you do is you make that the identity vector, right? So you'd have x dashed A would be the identity vector plus, and if you want it to be a spatial translation, then it would be some vector of the form not A, B, not A, PQR. Those are the space component, and that's a spatial translation. Okay, and it's in that form. If you want a time translation, that's easy. You just make those 0 and put some other number there, M or something. That's a time translation. Question?
Since we are dealing with time in a different sense here, and we are altering or maybe assumptions about time.
Yeah.
Can we say that we can perform time translations with within this theory?
With what? Sorry.
Within this theory. I mean, we obviously perform them. But
yes, we have a.
Why doesn't there arise some issues with time translation?
Yeah. So I didn't emphasize enough that it's legitimate to use the idea of a time translation because we are imagining that the two frames of reference have identical clocks. I agree, if you were not allowed to make identical clocks, then there would be lots of difficult questions, right? What does it mean to compare this clock with that clock when you've no idea how they are measuring time, you see? But there's a sort of implicit assumption that actually in some books it's made perfectly explicit that you are allowed to have identical clocks. This is reasonable because most of our atomic clocks are based on the frequency of certain spectra, atomic spectra. And so it's reasonable to say, okay, well, if you've got some cesium and somebody else has got some cesium and you've both got it at a similar temperature and you're looking at the spectrum and you're using that as your clock, then they're identical clocks.
Okay. Can we say, clearly we can say, but we can say that there doesn't arise any issue in translating time that alters the time somehow. It's not self-referent in that way.
I think that comes back to, so your question is, how do we know that we are not allowed to do something other than a translation? Right? Maybe that's what you mean. And the answer to that is, if you did something else like t dashed equals t squared, right, then it's not linear transformation anymore. And it has to be linear because of the inertial frames.
I see.
Okay. So I think that really does leave you with translations in time. Okay. Okay, so I was arguing that this expression here can do spatial translations, time translations. It can also do rotations, because for a rotation we make that 0 and we choose here a matrix which performs a spatial rotation. So it would be a matrix where you could rotate in y and z, for example. So you'd have cos theta, sine theta, minus sine theta, cos theta. That's a rotation in the yz coordinates, and then you leave everything else alone, for example, right? And you could make up similar things for other rotations. And so this expression here can easily do spatial rotations, it can easily do spatial translations or time translations, and it can do the standard Lorentz transformation. In other words, it can do all of those things, and so it can do the general Lorentz transformation. But there is a condition on this matrix. It's not any old matrix here. If you just wrote down some arbitrary matrix here, it would not necessarily be a Lorentz transformation. So there is a condition on this matrix. And the condition is that that this transformation, have I missed something out? Just let me pause for a minute. Yeah, I have missed something out. Right, so I'm going to find out what are these matrices? What is the condition on these? And when I do that, let me just check the time, because I think I'm running out of time, aren't I? Oh, I am. Just let me think for a moment. Yeah, I prefer not to rush this. So what I'll do, I'm sorry, is I'll stop here. I'll leave you hanging. What is the condition on M? But we'll find out tomorrow. Okay?